Hello guys, welcome back to my channel Physics with Sebbi. Today I am going to present an amazing problem from rotational kinematics. Let's have a look at this question. Two identical circles of radius r intersecting at point P with constant angular velocity omega. The other point of the intersection Q is originally at a distance d from P. Find the speed of Q as a function of time. Please have an attempt before going to check out my solution. Take a glance at my solution. It's a wild one to imagine, so I came with an captivating animation. Let us dive into the problem without delay. In the problem it is given that one circle is fixed and other circle is moving with angular speed omega about this point P. Here you see this green circle is rotating with constant omega about this point P in a circular path. Once again you see it is moving in clockwise direction. Here two points are there. One is intersecting point P which is fixed, other intersecting point is Q. We have to find out the velocity of this intersecting point, isn't it? If you observe that the intersecting point is moving along this circle of radius r with some angular velocity, but it can be noticed that when this green circle completes one rotation, this intersecting point also completes one rotation. It appears that the angular velocity of this circle is equal to the angular velocity of this intersecting point. But we don't know that omega is constant or not for this intersecting point. If it is constant, then we can write velocity of this intersecting point as Vq is equal to r omega. But we don't know omega is uniform or non-uniform. So we have to follow the procedure to find out the velocity of point Q. The velocity of point Q is found in a tricky way. That is nothing but we are considering a frame of reference which is rotating about this point P in clockwise direction. Means in which direction this green circle is rotating, in the same direction the reference frame is also rotating about the same point P. But this reference frame is rotating with angular speed omega by 2. The angular speed of this green circle in the clockwise direction is omega with respect to the ground frame, but with respect to this rotating frame it will be omega by 2, isn't it? But this fixed circle is also rotating in counterclockwise direction with omega by 2 about the same point P. You can see the animation of them. Both are rotating in opposite direction with the same omega by 2, isn't it? At this time what happens, isn't it? You see the intersecting point is moving in a straight line. Means with respect to the reference frame we have to find out the velocity of Q along this black line direction. To find out the velocity of intersecting point Q, we have to consider this structure. AB are the centers and PQ are the intersecting points and D is the distance between the intersecting points. R is the radius of the circle. From this triangle, here you see this angle is theta. Cos theta is equal to D by 2 by R. Cos theta is equal to D by 2 by R. And theta dot is equal to minus omega by 2. Here, this radial line makes an angle theta with this black line. This theta changes with time, means the changing theta with time gives the angular velocity of this red circle in the counterclockwise direction. Therefore, I write as the angular velocity of the red circle is equal to minus omega by 2. Here minus y we have to write, means as time increases this theta decreases, therefore I can write minus omega by 2, or otherwise we can say that it is moving in counterclockwise direction, so we can write minus. Differentiate this with respect to time, we will get like this. Finally, velocity of Q with respect to the rotating frame along this vertical line, and it is given as d dot is equal to r omega sine theta. From this equation we can write like this. D dot means the velocity of q with respect to p. D changes along this line with respect to point p. But we require the velocity of intersecting point q in ground frame. When we come from rotating frame to ground frame, we can see this extra velocity of intersecting point in the horizontal direction. That can be written as the distance of intersecting point q from the fixed point p is nothing but d, and the angular velocity of rotating frame, that is omega by 2. The product of these two gives the velocity of intersecting point q in horizontal direction, which can be written as 2r cos theta into omega by 2. By simplifying that, r omega cos theta. Now the resultant velocity of the point q in the ground frame can be written as vq under root of vertical velocity square plus horizontal velocity square. We will get r omega, where omega is constant, means which is independent of time, which is uniform. Therefore the speed of intersecting point q is also constant, which is independent of time. This is the solution of this problem.